And this. Yeah. Okay, so let me get back to where I was at the end of the last class. So I'm gonna just go quickly through the last couple of things that I was saying. So I was looking at other more models of semantics that have been used in generative linguistics, where you have a little more structure on the semantic side than just the basic topological proximity and interpolation that we were considering before. And so one of the cases that I discussed last time was this Piotrowski semantic, which basically construct an analog of merge on the side of semantics, which we've seen that if one wants to make it compatible with the free symmetric merge, essentially this reduces it entirely to the free symmetric merge mapped into semantic space. And so the image of the syntactic objects inside semantic space, as we had already seen before. Something that's a little more elaborate is what I started talking about at the end of last time, which is the Heim-Kratzer model of semantics, which is based on the idea of having some kind of logic associated to semantic space. I'll say a bit more later in what sense one relates this to logic, but another way of just saying what the construction is, what they do is they form a semantic space, which is based on a collection of types. And these types are defined inductively in terms of functions, spaces of functions. And the idea of is that ultimately these functions end up being evaluations into this set of 0 and 1, which are assignments of truth values. And so it was a way of, in a sense, thinking of the assignment of truth values to propositions, which is something that is a kind of computational operation that we do, the sort of logical calculus that we do. And it's not part of just the computational system of syntax that we have discussed before. So their point of view is that that's what the semantic side contributes. And so in the way that they describe this assignment of truth values, of course, as functions to the set of 0 and 1. But the domain of these functions themselves are inductively are going to be sets of functions themselves. So let me review briefly what I was saying. Yes, is there any question? Okay, so one starts with the type of individuals and a set, which are all the possible denominations of this type. So the idea of that there's a set of all the means like all things that are individuals, right? We can view it that way. And the other basic type that they start with is indeed the truth values, 0 and 1, this type of truth values. And so the first thing that one can do is form functions from the set of denominations of individuals to the truth values. And these are just assign the truth value to something being a certain individual, right? So and so the level set one of such functions are all the individuals for which that evaluation is true. And then once you have this type of functions from the to the t, you can inductively form other types by saying that if you have already constructed a type sigma and a type tau, the type sigma tau is functions from denominations of sigma to denominations of tau. So you get this this semantic space, which is just a union of all these sets of functions, all these inductively constructed. So this is, of course, a huge set, right? Because you can keep inductively constructing such, given any two types that you already have, and you take all possible things constructed this way. So unlike the examples of semantic spaces that I have discussed before, which are kind of fairly small in the sense that we assume that there's some finite dimensional, Riemannian piece of a Riemannian manifold or a vector space, finite dimensional vector space. And so something much simpler that way. So that would be more like what you can imagine this first set, DE, this set of the dominations could be assumed to be something like that. Some finite dimensional vector space, for example, or some metric space. But as soon as you start to inductively construct spaces of functions, you end up with a very large and an infinite dimensional thing. So this looks quite different from the previous models of semantics that we looked at. And so we can try to see how this type of model of semantics can fit with this idea that I was describing of thinking of mapping of syntactic objects and parsing of syntactic objects as some kind of character from your algebra workspaces to your semantic space, endowed with some kind of filtering like a Rothenbuchster operator and so on. So this again, I mentioned this last time. If we want to start setting things in our framework, we can assume that the lexical items are mapped to this semantic space and have corresponding values, which we can assume are in this set of individuals that we start the inductive construction of types from, for example, or they could be already functions, depending on what the assignment is. And we want to extend it to syntactic objects, not to individual, just to lexical items. And so the way that this is done in the Heim-Kratzer semantics is by saying that you can do that. So a certain syntactic object is parsable from the point of view of this form of semantics. If you can, when you think of, so this is an inductive definition, so you split your tree into two parts by merge, and it's parsable if when you put them together, the corresponding values that you already have of the two subtrees, one of them is a function that can be applied to the other as a domain. So for example, if your so this is symmetric because it can be either one of them that can be a function of the other. But for example, say that if S of T2 is in the denomination of some type sigma, then S of T1 has to be denominations of something that goes from sigma to some other type tau. And when you combine them, you apply your function to the other argument, so you would get something which is a denomination of type tau. And so if this happens, it's parsable, and otherwise it's not parsable. Okay, so we can think of this as again as a character, in the Boolean, with values in the Boolean semiring, because here ultimately everything ends up being an assignment of 0, 1 values. So the only semiring in which we can do parsing with this point of view of Heim-Kratzer semantics would be just the 0, 1 Boolean semiring. So there, we don't have any filtering except the identity Rothenbuchster structure. And so the only character that we can construct is the one that checks if something is parsable or is not parsable according to this notion of parsability of the Heim-Kratzer semantics. And so if we do this, which is just this simple-minded thing that is simply encoding this definition of what parsability means. But then, what does it mean to take this Bogoliubov preparation that looks at all the substructures at the same time? So this is doing something. So what it's doing is to actually check, in the case where something is not parsable, it's actually locating the substructures that are parsable and the maximal combination of substructure that is still parsable, even though the entire thing is not parsable. If not parsable, it means that at some node, this matching of function and argument is not happening correctly. But no, this combination of is exactly isolating all the parts where the matching is happening correctly, and identifying where things go wrong. So it's again a sense in which this operation, the coproduct operation of extracting all the substructure, is actually locating the difference between where things are okay and where they're not in the parsability. And in all of these cases, including this one, the key thing is that these parsability operations, in a sense, are local. So they are happening or not happening at certain particular location in the tree. And so when you break into substructure, you are actually able to locate where the problem is coming from. And in the sense, this is another sense in which the situation here is similar to what is happening in physics. In physics also, a lot of things depend on the fact of being on what you are computing being local. And it is and here this is exactly reflected on this compositionality properties in both in syntax and in semantics, and say that whether something parses or not is not over the, so it is located on certain substructures, in general. Okay, so the one thing that one can try to do, so the original formulation of the Heim-Kratzer semantics, I mean, I put the original text on the web page if you want to see more about it. I gave a very, very sketchy, quick review here. Is, as I said, only set theoretic. So all of these function spaces that are defined this way are just set theoretic functions. There's no topology on anything. But it's sort of natural to assume that, for example, if we start with a certain type of denominations, it might have at least some of these proximity structure that you want to keep track of, to say when two things are closely related to each other, when you assume that semantic values would have to be locally constant, or if they have 0, 1 value, then anyway continuous, when you move in a small neighborhood of a point in your semantic space. So one can try to find a way to topologize these Heim-Kratzer types, so that one can also include the possibility of having proximity relations and interpolation in these semantic spaces. So one has to be careful because these are very large spaces and they're function spaces. So one can assume to begin with that the first set that you consider, these denominations of individuals, is as nice as you want it to be from our perspective of these basic topological properties of semantic spaces. So for example, we can assume that it's a geodesical, convex, compact Riemannian manifold, as we have considered before. And so basically here we have that it's metric and that it's compact. And these two are nice properties from the topological perspective. And it allows for both proximity and for interpolation. And well, the other basic type is just a discrete set of just 0 and 1. So there's not much that we can do in terms of topology. That's necessarily a discrete set. But so the first thing we notice that the next step is that you want to take functions from, say, this set of DE of individuals to 0 and 1. Well, of course, this if you require now we're trying to make topological spaces, so the natural requirement is that this will be continuous functions. But of course, continuous functions with values in 0 and 1, they're just constant or connected components, necessarily. And so if you start with a compact, compact metric space that happens to already be compact, that to be already connected, then you just get constant functions. Either everything is 0 or everything is 1. So there's nothing interesting anymore in this first step of this inductive construction of types. So obviously that's not the right thing to do, right? So so maybe we're gonna say, okay, just requiring that this would just this function would all be continuous is a bit too much. Maybe there's not there's reason to that maybe we do want some possibility of discontinuities in these evaluations, which does make sense in many ways. But on the other hand, at the opposite extreme, if you don't topologize at all the space of functions, so you take all possible set theoretic functions, you get the power set of this set, because then you get all characteristic functions of all subsets of this D, and that's an enormous set. And also these the power sets are actually not so nice to topologize as to make into topological spaces. And so you want something in between, or something that's a subset of the entire power set that is non-trivial, so it's not just everything or nothing, but is that can be topologized nicely. So it usually in various situations in topology, it's natural to take the functions that are characteristic functions of compact subsets. So it's like saying that, okay, you're gonna have things that are locally constant on a compact set. So, but there can be discontinuities, as you can jump when you read the boundaries of your compact set, but it's not all arbitrary characteristic function of arbitrary set. And so this actually is a fairly nice space to consider. And so one can say that maybe a proposal for a topological version of the type of functions from the tau to the t is or the e to the t is the set of all compact subsets of the, which is the same as all characteristic functions of compact subsets. And so the reason why I'm saying that this is a nice space is because now our DE is a compact metric space, and this new topological space of compact subsets D is itself a nice metric space with the Hausdorff metric. And the Hausdorff metric is simply comparing two compact subsets by how close they are. I mean the explicit expression for the distance, maybe it takes a moment to parse, but basically what you're doing is you take one of the two. One way to think of it is that you inflate it until it contains the other one, and vice versa, and you say what is the minimal of the two. And or another way to see it is like what is the maximal of the differences between the two sets, right? Of the distances between the two sets. So this is also if so this metric space has really nice properties in general. So the good thing here is that your first space of functions that you're considering has very close topological properties to the set that you started with, this DE. So you still get something that's metric, that's still a metric space, and has a nice topological properties. So one thing to note, which I'll be useful in a moment, is that if you start with a set, so here we start with this set DE, which is which we know is metric, is compact. And if we're just if you start with another set X, which is not necessarily a metric space, but is a topological space, you can still form the set of all compact subsets. And it's not necessarily metric. So you cannot, you see the Hausdorff metric here is using the metric on the underlying DE. And so if you don't have a metric on the underlying DE, you can still define a topology using this Vittorius topology. This is okay. It's one of these long stories of that one usually encounters in problem sets or point set topology, like this hit and miss type topologies. And so it's a topology that's generated by two classes of sets that somehow they tell you whether you meet how much you meet a given open set and miss its complement. So a certain class of open sets are the ones that don't intersect a certain so all these are, you're looking at the set of compact subsets of X. So this is the points in this space, so the compact subsets that don't intersect a certain fixed open set, and those that are contained in that. So either they totally miss it or they are completely contained. And this use this as a basis to generate the topology. So this looks quite different from what I've shown in this here in this case with the Hausdorff metric. But it's in case in which your space is metric, your space X is metric, the Hausdorff distance is exactly inducing this same topology. So it's just a more a metric-free way of writing the same topology. So this just to say that this space of compact subsets can be topologized in a nice way. And so more generally, we are looking at spaces of functions. If I look at if I have two well, let's say a priori just two topological spaces X and Y, and I look at continuous functions from X to Y, and what are nice in general, what are nice kind of topologies that you can put on these spaces of continuous functions. The main topology that is has good properties is called the compact open topology. And this is generated, again, you give a basis for the topology, so generating a class of open sets. And this would be those, so these are your generating open sets are parameterized by the choice of a compact subset in the source and an open subset in the target. That's why it's called the compact open topology. So for every choice of a compact subset in the source and an open subset in the target, you get a generating open set of the topology of the space of continuous functions. And these open sets consist of all those continuous functions that map the compact subset of the source inside the open set of the target. So it's a picture like this. So you fix a certain compact sets in the source, you fix a certain open set in the target, and you look at all the functions. So functions that are in this neighborhood, they can differ a lot outside of this rectangle, but their graphs are all inside this, are closed inside this rectangle. So they are, and outside of this rectangle, they can differ as much as you want. So that would be those functions that are have this property that they all pass through this rectangle form these open subsets. Okay. And one of the properties that this topology has is that if the source topological space is compact, and the target topological space is metric, then there is this space of continuous function is itself metrizable, and the metric is the sup metric, the supremum over the points. So you you take the sup of the distances. So now the thing is this, though, that if you are in this case, right, that x is compact and y is metric, then you get something that's still metric. Note that you will not get something that's compact, because there are characterization of compact subsets of function spaces, like for example with this sup norm, like the Arzelà-Ascoli theorem. But in general, you expect compactness to be very rare, in function spaces. So, and it's the first thing that you lose in this inductive construction is going to be compactness properties. But then it's clear that you're doing an inductive construction, right? So at the first step, even if you have like source is compact and target is metric, you get that you keep metric and you lose compact. But then at the next step, you have lost compact, so you can also lose the metric property, because you will not have this anymore. So the observation is that even if you use like the most well-behaved type of topology that you can put on these spaces of functions, and you start with the first one, the E, that is as nice as possible a topological space. When you start to make these inductive constructions, you will very quickly lose both the metrizability and the compactness. You will still have topological spaces. So except that working with topological spaces that are not metrizable and non-compact is more difficult than working with nicer type of topological spaces. And so here it's kind of the way that things go. To what extent you can keep properties. So let's say that now we want. So I'm gonna now decorate all my semantic spaces with this, with some additional thing that reminds me that I'm not looking at them just set theoretically anymore, and I'm trying to put some topological structures on them. And so I start by assuming that my initial is a topological space that is metric, complete, and compact. And the first step will I take with values with in the truth 0 to value 0, 1. I use this space of compact subsets. There are characteristic functions of closed and well, it's the same closed or compact subset because you're inside the compact space. And this has a Hausdorff metric that is both complete and compact. So up to this point, I'm keeping the best properties I have. And so this now I have that this is compact and this target is metric. So sorry, this should have been for going from E to this other type remains metrizable. And so I can, for a while, I can keep at least one of the two properties. And so in some cases, like if I keep this kind of, so some inductions will be able to maintain at least one of the properties, the metrizability, but not the compactness. But other inductive types will also lose the metrizability. And so if I have, like, for example, if I have constructed, take something that I already know is not lost, where one of which for one of these for which I know I've lost already the compactness, and if and even if the target is metrizable, I cannot guarantee the metrizability of the corresponding function type. Okay, so nonetheless, I mean, this is the best that one can do in this way to try to topologize these types. And again, one can try to then build some kind of other characters, algebra characters in this setting. So, for example, one can try to build probes, that can test, with this, yeah, can test parsability with respect to some hypothesis, some probe. So, for example, what is a probe in this setting? We were saying in the vector space model of semantics, and I did the example a bit earlier. What I can think of a probe is just to pick some vector and then see whether the vectors assigned to various structures are how much agreement or disagreement they have with my probe, and have a filter that eliminates those that disagree with the probe and keep the ones that agree with the probe or have some degree of agreement or disagreement. So here I'm not in a vector space, so I cannot compare vectors, but for example, I can think of a way of constructing probes by choosing a certain family of compact subsets of inside a given denomination of types, and I can make so I have these characteristic functions of those subsets, and so I can test belonging to these subsets by evaluating the characteristic function on whatever my my element like that corresponds to just certain structure. So it means that if my structure T is mapped in this that's a semantic to a certain denomination of a certain type, I can test whether it belongs to certain compact subsets in that type. And of course, it would be zero if my probes are in the wrong type. Okay, and again, it's one can do this, and your Bogolubio preparation that checks the various substructures will identify nested chains of substructures where the probe evaluates true on all of the terms. So it would be finding all the substructures that match this particular probe, so that end up in the particular compact region of my very large space of the denominations of a given type. So one other way to think about how to topologize the Heim-Kratzer semantic, which at least removes one step that's a bit more complicated in what I said. I mean, what I said, you have to actually do something to take care of this fact that when you take functions in 0, 1, you have to select a collection of functions that are not all functions, but are not just continuous functions, because otherwise you just get things that are constant on connected component and nothing more than that. But a more maybe a more natural way to do this passing from set theoretic Kratzer types to topological Kratzer types is to actually also replace the truth values 0, 1 with some kind of intermediate possibilities by allowing truth values that are in the interval 0, 1, so some kind of fuzzy truth values. And then this assignment of truth values becomes a fuzzy structure. So a fuzzy set is by definition a set endowed with a function from the set to the interval 0, 1, which is usually interpreted as some kind of degree of belonging of a point to the set, right? If you have a function with values exactly in 0, 1, it's the characteristic function of a certain subset. It just detects belonging to that subset or not in a 0, 1 way. But here you allow for degrees of belonging. So you can say that you introduce you start with the same set of denominations of individuals, which again we can assume is a topological space, as nice as you want it to be, and you take instead of the truth values as the other basic type, those 0 and 1, you take these fuzzy truth values. So the denominations are now the interval 0, 1. And so the type EF would now become functions from the denominations of the individuals to fuzzy types. And now it's perfectly okay to take continuous functions. You don't have to go through this, taking characteristic functions of compact subsets or and so on, because now you have a large supply of continuous functions with values in the interval 0, 1 that are non-constant. So you can just uniformize this construction of types without having to make a separate case for where your target is discrete. You can just always take continuous functions as your space of types. And so in this case, all of these will get topologized with a compact open topology, as I described before. You have the same issues about the fact that compactness and metrizability, necessarily at some point get lost in these constructions. And for some things you can keep metrizability, but not for all the types. And you can similarly do this kind of semantic probes by using instead of our in the example I gave before, I was using a choice of compact sets as semantic probes, which meant a choice of characteristic functions of compact sets. Here, instead of characteristic function of compact sets, we have continuous functions, so to the interval 0, 1. So, a semantic probe is a choice of a bunch of such continuous functions. And now the parsing is not happening anymore in the Boolean semiring of just 0 and 1. Now it's happening in the Viterbi semiring, which is just 0, the interval 0, 1 with the maximum and the product as a semiring structure. And there you do have a non-trivial Rother-Baxter structure, which is the thresholding, which now makes sense because you're allowing intermediate values of between 0 and 1. And so you can say that you accept with a certain confidence. So you put a threshold and you assume that your truth value is anything that has a fuzzy truth value, which is at least a certain threshold, like this. Okay, so you get this corresponding notion of fuzzy, Heim-Kratzer interpretability, which would give you, an assignment that follows the same original rules of the Heim-Kratzer interpretability, meaning you have to have functions that compose, but now are continuous functions that compose, and so everything is to be compatible with the topologies. And so if you use this possible probes and the parsing, you can get associated characters. We just check check the probe on the values that you have constructed by the Heim-Kratzer parsing. And again, with respect, when you cut with this threshold, your Birkhoff factorization will extract as maximizer those accessible terms, or chains of accessible terms, where all the values are above the threshold that you put. So it will identify like the largest chains of substructures where your truth confidence value is sufficiently large. Okay, so as I said, this more general type of models of semantics that contain type of additional structures that I discussed here, where this Piotrowski semantics, the Heim-Kratzer semantics, And there's also some older discussions about semantics in generative grammars. I put all of this on the web page, so you can access them there, all of these references. So there's one more thing that I want to discuss, about these models of semantics, and this idea that I just mentioned in relation to the Heim-Kratzer semantics, that one expects that semantics should be responsible for the logical operations in some sense, and that's why very often people in linguistics who work in semantics, semanticists, they're not so happy about the very simple models of semantics where you only want to account for some kind of proximity, like the vector space models of semantics that are used in computational linguistics, because they want the side of semantics to be also accountable for some kind of logic. And we know that the model that we are given of the computational mechanism of syntax, well, is a computational mechanism, but is not it does not have logic encoded into it. And so one has like where this logical operations are taking place, in all of this model. So one thing that I want to stress is that if one starts by this very minimalistic view of how a semantic model can be built, where we can say, well, we assume the semantics is at the very heart just a topological relation of proximity, interpolation, distances, agreement, disagreement, this kind of structure. So we assume that we have some kind of topological space as our semantic space, but we don't assume that it carries any additional structure beyond that. So what I want to argue is that that is actually, in fact, sufficient to also get for free a logic. And so I'm gonna just review very quickly why that is the case. And so the main idea lingered on the slight difference that there is between two notions of logic. One is a sort of classical Boolean logic, and the other is the constructive logic that or Brouwer logic. So I misspelled it, Brouwer. So let me start with the Boolean, the usual sort of Boolean logic. Well, a concrete Boolean algebra, is very easy to realize. You take a given set and you look at the subsets of a given set, like, and you look at the usual set theoretic operations of union and intersection and complement. So you can, the typical example of a Boolean algebra is the power set of a given set, the set of all possible subsets. And these are enough to give you all the basic logical operations, because the intersection of sets gives you the logical AND, and the union of sets gives you the logical OR, and the complement gives you the negation. And the other logical gates are just obtainable as composition of these basic logical operations, as is known. So you get all the usual logical gates as in terms of purely set theoretic operations, which you can write as the corresponding Venn diagrams if you like pictures, and that's the usual very basic setting of Boolean logic. And for example, the logical implication is also a set theoretic operation. We take the complement of the set union D. A implies B means A complement union B. And this can be abstracted easily, and you can say that an abstract Boolean algebra is a partially ordered set that has two operations that are associative and commutative. They join and meet, usually call them that way. And so they satisfy a list of properties. One is the way that they relate with respect to the ordering, and the idempotent property of both operations, the absorption law, and the distributed law. So it's as you can see here, right? There's kind of a complete symmetry in the way these laws are stated between these two operations of join and meet. And in particular, also a Boolean algebra has a complemented property. So there are zero smallest element, least element, and one greatest element with these properties with respect to the two operations. And every element has a complement which can be described in terms of these least and greatest element and the two operation. And in particular, a Boolean algebra satisfy de Morgan's law, which has these two dual forms. Again, everything here is completely symmetric with respect to the two operations and the 0 and 1. So you can like flip everything and have the Boolean property preserved. And other properties of classical logic, classical Boolean logic, are the cancellation of the double negation and the law of the excluded middle, either A or non-A. And the law of non-contradiction. You cannot have both A and non-A. And these are the law of excluded middle is just the complemented property of the Boolean algebra. Okay, so this is like the very basic classical logic, right? So at the very least, if you want something to account for logic, you would want to see some construction of logical operations of this kind. But here's the point: maybe not exactly of this kind. There is another way of thinking about logic, which is not exactly the Boolean logic. And that is constructive logic, which is also referred to as intuitionistic or Brouwer logic. And so the idea here is that in classical logic, propositions are always assigned can always be assigned some truth value. The law of excluded middle says that this is always possible. At this basic level of propositional calculus, of course, there's other stuff that I'm not talking about, no Gödel, but and in constructive logic, propositions are only assigned a true value if there is a constructive proof. So if there is an algorithm that gives you this is an algorithm that constructs. And so you say that the proposition is inhabited by a proof if such an algorithm exists. And in particular, this means that you don't necessarily have this excluded middle anymore. And also you don't, in general, necessarily have the cancellation of the double negation. And of course, this can hold in specific cases, but not in general. So the punchline is that the basic object that replaces the Boolean algebra in constructive logic is a Heyting algebra. So the abstract definition of a Heyting algebra, it kind of follows the definition of a Boolean algebra up to some crucial difference. So you start in the same way. You have a partially ordered set, and you have two operations of join and meet as before with minimal and maximal elements. So with the same basic properties, but you don't have the complemented property. So one assumes the existence of what is called a relative pseudo complement. So if you take any two elements in your Heyting algebra, there is a greatest element, greatest with respect to this ordering structure. There's a greatest element with the property that A and C is less than or equal to B, and you call this the pseudo complement of A and B. And so this gives you, the pseudo complement is designed to give you a replacement for what the logical implication is in the Boolean sense. And so instead of taking, A complement union B, now you say that the A implies B is this, is defined to be this relative pseudo complement of A and B. And now if you take this as your definition of what the logical implication is in a Heyting algebra, then you have a corresponding pseudo complement, which replaces the negation, so the complement of A in the Boolean case. And so the pseudo complement of A is just the implication A to 0, implication in this cell. So it's psi of A 0. So the negation now is not defined as the complement in the set theoretic sense that we have in the Boolean algebra, but it's defined as this pseudo complement. And so now the point of doing it this way is that this has most of the same properties as the Boolean algebra, except that you exactly allow more flexibility when it comes to these particular properties like the law of excluded middle. So the law of non-contradiction still holds exactly as in the Boolean case. But now the law of the excluded middle is no longer in general true if the negation is given by the pseudo complement. And the pseudo complement and the implication now satisfy this relation. So in the Boolean case, the implication, as we've seen, was the complement of A union B. And now you only know that complement in this pseudo complement sense, union B is just less than or equal than the implication in this Heyting sense. And in fact, it happens that if this inequality is always saturated, so it's always actually an equality, then this really is a Boolean algebra. It's not just a Heyting algebra. And the other main modification that you have is the Morgan law. Now the Morgan's law are no longer symmetric. You still have one of the two, the Morgan's law, that holds exactly as in the Boolean algebra case, but the other, the Morgan's law, becomes weaker because now the double negation is no longer canceled. So the other one has the explicit double negation, which is not necessary, doesn't necessarily go away. So okay, if one just states it in this abstract form, this is a little puzzling, right? In the sense of where it looks kind of pulled out of the hat, where do these relative pseudo complement and term come from? However, the thing is that concrete Heyting algebras are extremely easy to find. They are just topological spaces. So they're just the open sets in a topological space. So just as Boolean algebras are subsets of a set, the prototype examples of a Boolean algebra is the power set of a set. The prototype examples of a Heyting algebra is the open sets of a topological space. And here you see immediately why all the symmetries that you have in a Boolean algebra are not necessarily there anymore, because of course the notion of topology is not symmetric with respect to taking complements. Open sets and closed sets don't behave in the same way in a topological space. And whereas, sets and their subsets and their complements behave, in exactly the same way as set theoretic, subsets. So what happens with the implication and the pseudo complement here is that they have a very simple description now in terms of topological operations. So instead of being, if you were just in the set theoretic case of Boolean algebras, you would say that the implication is A complement union B. But here, you don't take A complement union B, you take the interior part of A complement union B. The interior is like the largest open sets that contained in this set. The point is that, of course, this itself, so we are working with open subsets of a topological space. And if A and B are open subsets, well, the A complement is a closed subset. So this itself is no longer in the class of open sets, but the interior is like the largest open sets that's contained in it. And so you see why you get this implication. And so you get this so it's something that's kind of smaller, right, than the and in the same way, right, the pseudo complement is not the complement set theoretically, because the complement set theoretically is no longer an open set. It's the interior of the set theoretic complement. And the thing is that so all the properties that this constructive logic work for open sets of a topological space. So this one can worry about whether trading Boolean logic for constructive logic is problematic. Of course, Boolean logic is in a sense more powerful than constructive logic. On the other hand, constructive logic is really the basis for several important parts of mathematical logic, in particular type theory, like Martin-Löf type theory, which I will not talk about. I mean, this is kind of related to this. I mean, the Heim-Kratzer inductive construction of types is modeled on type theory in the logical sense, and is it is designed in a way to incorporate type theory into semantics, and so the Heyting algebras should be the natural setting for doing this, because Martin-Löf type theory is based on constructive logic, and also this kind of more interest to mathematics per se. All of the recent very interesting work on homotopy type theory incorporates Martin-Löf type theory and is also based on the use of constructive logic and Heyting algebras. So this in many ways, it's not unreasonable to take that this is the class of logic that is most natural to consider. So the punchline of this this digression here is just to say that if we make this very minimalistic assumption about what we want semantics to be, it's where we only assume that on the side of semantics we have some kind of topological space. It does not mean that we renounce to the having also a logic there, because the topological space generates its own logic, which is in this form of the associated Heyting algebra. Okay, so this part I think is all I wanted to say. So I'm gonna switch to the next thing that I want to talk about. And I get my next set of slides.
So is it correct to say that every topological space generates this kind of logic?
Yes, that's exactly the point. Yeah, that's exactly the point that I wanted to make, that each topological space generates its logic. So it's a logic of this form, a logic of this constructive type. And so the point is that you don't have to worry about also imposing as additional structure that you have logical operations on the type of semantics, because if you assume that you have a topological space, you also have a logic. Okay, so there's one more thing that I want to talk about that has to do with parsings of syntactic structures, which is semiring parsing. And I will also add, which I haven't. So I added various references to the web page. I still have to add a couple more, and I also want to add some about this semiring parsing story, which I haven't done yet. But this is also part of this. Okay, but so the idea of using semirings to parse syntactic or structure generated by a generative grammar. So, so let's say syntactic objects in this more general sense goes back quite a long time. So this relation between generative grammars and parsing in semirings was introduced in these papers of Chomsky, Schütz, and Berger. That is actually on the web page. They contain several very nice results. So, if someone wants to read that for their presentation, there's a lot of interesting, very nice mathematics in that paper, in several famous theorems. And so, but one of the things that does is introducing this idea of parsing by semirings, and in that formulation, it was based on using context-free grammars. And of course, here we want to use merged as the generative process of syntactic objects that we have seen instead of formal language. So one of the main ideas about how this parsing in semirings works is that you wanna follow derivations for certain structures, and certain, well, in the case of formal languages, you have a derivation for a certain string in the language, and you think of the steps in the derivation as your substitution rules in the formal language. And the way that this is often formulated in this formal languages setting is that you write certain deduction rules that have a certain standard form. So you write them as a kind of numerator and denominator part, and something on the side. And the meaning of these expressions is that you have on the what you write in the denominator, in the numerator here, is certain rules of the generative grammars and certain inputs, certain non-terminal inputs that you can use for your derivation. And you have certain kind of side conditions, which are usually Boolean, in the sense that is something that tells you that when certain conditions are met, you can do a certain derivation. So they're like controls. And then what you get down here in the denominators is then is a possible deduction. It means that if whatever you have in the numerator parses subject to these conditions, parses correctly in your parsing semiring, then it will imply that what you have in the denominator also parses correctly. So that's a way to actually follow chains of derivations and check. Again, is a way of checking consistencies, right, in the sense over substructures, but with a different formulation. And so here the way that these evaluations for whether something checks or not are performed is that whatever you have up here is mapped to a semiring where the corresponding values are combined with the semiring operations, and the obtained values is assigned to the output that you are deducting from these operations. Okay, so I'm not going into the details of how this works for the context-free grammars. I will actually put a paper on the page that discusses exactly this setting that I wrote here more in details. It's a bit different from the original one of Francis Zabarsha. And it has various examples of valuations in different kinds of semirings. So I'll put it, I'll make it available there. But in a sense, the idea here is, what if I want to do something similar in case of merge? So we're seeing that what a merge derivation is, the way we were discussing the action of merge on workspaces was constructed in this way. You start with a workspace that is just a collection of your lexical items. So, trivial trees that consist of a single leaf with label, or a big forest that consisted of components that are just labeled leaves. And then you start, iterating the operations of merge in whichever way it's possible to apply them. And you get this start to form structure. So you have forests that have now components that are non-trivial syntactic objects that you can assemble together with merge. And you want to map this to some kind of test for parsability of these various structures as you go through the chain of derivations. So what is the good formalism for doing that? For doing this kind of parsing. This is a bit different from the kind of characters of algebras that I've discussed so far, because there, I'm not looking at the steps of forming structures. All the parsing, the type of parsing that I've discussed up to now, were of a different nature, in the sense that I take a structure that's formed, and I have some characters from my Hopf algebra to some semiring, and I want to use that to break down into substructure and try to understand where there's some substructure that either works or does not work. This point of view is a bit different. Is about following the chain of derivations that builds the structures through merge, and try to see along this chain of derivations how the parsing is happening. Okay, so I'm gonna give various perspectives here. I'm gonna go through a few different things that are related to this question. So the first thing is a kind of, let's say, warm up case. I'm gonna go back to the discussion I did a while back on this minimal search, minimal yield. So these conditions that were selecting certain merge derivations as being better than others on the ground of how they transform the workspace. So these were this argument for why internal and external merge are dominant with respect to these other sideward forms of merge, because they are optimal with respect to some suitable cost function, or because they satisfy some constraints, like not increasing the size of the workspace, like convergence of derivation, and no information loss, and so on. So I'm gonna repackage. So I'm gonna repackage that type of argument, about selecting certain merge derivations as being nicer than others in terms of some cost function. In terms of some semiring and Rotobach's structure on these semirings. And now the reason why I'm saying this is kind of a warm-up step is because when I do this, this is kind of an intermediate step between the kind of parsing that I was discussing before and the kind of parsing that I want to discuss now. And so here is still, it's the case that I'm going to construct a certain ring of merged derivations, but I still don't with a Rotobach structure. But this I'm going to keep it as the target ring and still use a character from my Hopf algebra of workspaces, and that will filter out certain derivation and keep others. And the next thing that I want to do is that now I want the derivations to be the source rather than the target. So I want to not have the source just be my build structures, but also the derivation steps that lead to that build structure. And so I will have to modify the Hopf algebra of workspaces where the object of these Hopf algebra workspaces are the workspaces. So they are not the actual operations that go from one workspace to another. And so I would want to change that into something where the arrows themselves are the objects that I'm interested in, not the source and target of the arrows. And so that will correspond in algebraic terms to going from Hopf algebras to something that's called Hopf algebroids. Let's say what that accounts of. And then of course the parsing correspondingly, where we had something that works for parsing something that was going from a Hopf algebra to a semiring. And now we want something that goes from Hopf algebroid to there's some other stuff that gets one of these funny names, semi-ringoid with its own Hopf algebra. So this all gets very, very wild in this oid stuff. But so I'll explain. But it actually turns out, despite the funny name and the somewhat messy looking definition, this turned out to be actually very simple objects to describe because they are dual to very simple geometric objects such as graphs, directed graphs, which are, so they don't sound as fancy as semi-ringoids, but that's what they are. So, okay, so I'll start with, so this is kind of the plan for seeing some of this stuff. Okay, so let's go back to this example that I want to talk about first, which is revisiting some of these constraints that I was discussing earlier on about the merge and the constraints on the various types of merge. So when I describe the action of merge on workspaces, I kind of described a few different scenarios of what can happen when you apply our merge operation, this Hopf algebra Markov chain on one of the workspaces. So there's an external merge where it ends up being applied to two entire components of the workspace, merging them together and keeping whatever was any of the other component untouched. There is the internal merge where you extract a accessible term of one component and you merge it with the rest of the same component, and you keep whatever was not that component untouched. And then there were these other cases where you, for example, extract accessible terms from two different components, you merge the accessible terms and you keep what is left of the two separate components, and you keep whatever else you had untouched. Or you extract one accessible terms from one component, and you merge it with another full component, you keep what is left of the component from which you extracted, and you keep whatever was unchanged. Or you extract two different accessible terms from the same component, you merge them together, you keep what is left of that component, and you keep whatever was unchanged. So these were all the possible things that could happen, when you look at all the possible, terms that the merge is acting on. And the first two are external and internal merge, and the other are the sideward merge versions. And we were arguing that by two different type of arguments. One, about cost of extraction and deletion, combined, to give you a kind of grading of the terms of the coproduct, but with a weight that depends on the cost function, or by certain constraints on size of workspaces. These three remaining cases would be less cost effective, or violate some of the desirable constraints, and therefore external and internal merge should remain the dominant cases. Okay, so let's revisit this in a slightly different light. So let's go back to this counting of size effects on the size of workspaces that we used before. So I'm gonna recall a couple of things since I talked about it quite a while back. So let's say that the zero Betty number, so the number of so one thing you count is just the number of connected components of the workspace. And another thing you count is the number of accessible terms of the workspace. And you can also count the sum of the two, which is accessible terms, including counting components as being accessible terms of the workspace. Okay, and yeah, sorry, this is actually superfluous. It doesn't mean. So the three things that I wanna consider are the number of connected component, number of accessible terms, and combination of connected component, which is just the total number of vertices in the workspace, in the forest of the workspace. So suppose that I have a chain of merge derivations that I'm applying one after the other. And I want to look at the resulting effects. If I apply, so this is just one or more, after one or more applications of merge on a workspace, I want to see how these three quantities have changed as a result. So this minimal yield condition that I talked about a while back were designed to make sure that the size of the workspace doesn't explode along the derivation. So you assume that the number of connected components is not increasing, and the number, sorry, one of them should have been, yeah, I have a typo here. So you want the number of connected components to be non-increasing. You want the number of accessible terms to be non-decreasing, which is the no information loss, no syntactic information should be lost along derivations. So the number of accessible terms should be non-decreasing, the number of connected components should be non-increasing, and this number, the sort of balances, like one of them tends to grow, the other tends to decrease. So when you combine them together, you try to balance them in the minimal way. So this minimality of yield is like the minimal possible balance between these two constraints. Okay. But I mean, you can more generally relax this last one and maybe keep these two as the main constraints. So you can just maybe relax it to this non-negative yield. Also, we had discussed another kind of possible constraint, which was what I call this complexity loss constraint, which simply was following, like with each going back to this case here, each component, if you look at the root of that component. So you look at where it ends up, right? So for example, the root of these components end up in this component, the root of this component end up in this component, the others end up where they stay where they were. And here, for example, the root of this component ends up in this component, but the root of these components end up here, not here, and so on. So you keep track of like where each component goes, but in a sense of specifically where the root of each component goes, or what remains attached to that root goes. And one can formulate this type of constraint, which is to say that things should, so this should be an operation that builds more complex structures, right? And you apply it. So you want things to end up into being part of more complicated structures and not end up into smaller structures. So you want to make sure that if you impose this constraint, then we were discussing this fact that if you impose these constraints, well, certainly it's satisfied for internal and external merge, but in all the other cases, you do have things that start out into some larger structure and will end up into some smaller structure. And this would violate the idea that you build always towards more structures of higher complexity. Okay, so this is another of these structure building constraints. Okay, so how can we use these constraints? So let's build a kind of algebra on the merged derivations. So you can make a commutative associative algebra where the underlying vector space is just spanned by all the sets of possible merged derivations. So what I mean by this is I pick two forests, two workspaces, and a given set of possible pairs of syntactic objects. And then I look at whether there is a possible chain of derivation that uses these syntactic objects to form your merge operations that will go from one to the other of these workspaces. If there is such a chain, this is one of these objects. It's a collection of operations that goes from F to F prime. So I'm looking at like various possible ways that I can apply merge derivations to go from one structure to another. So I mean, you can think of it this way, right? For example, if I'm forming my structure starting just from the separate leaves with the lexical items, I can start to form some structure here, and I can start to form some structure there. Then I can combine these two together. I can combine these other ones. I can do this in various different orders, or I can do this like I can build different kind of structures with the same material and so on. So I'm looking at all of these possibilities, and each possible change that I can do is one of these objects. And then I just take as my commutative multiplication disjoint union of these that act on different parts of the workspace, right? So I can combine two workspaces. If I have something that acts here, I have something that acts there, I can make them act in parallel. So this is keeping track of operations that can be done in parallel on different parts of workspaces. And for that reason, it's commutative because if they're not mixing the material that they're using, they can be done in parallel in any order or in any order. And they will commute because they will not interfere with each other. Okay, and the unit is the empty forest. Okay, so I'll leave this here for next time, and I will do the maybe I'll finish talking about it next time. So I mean, next time I will still make the so you can still, if you want to, I think I should be able to be at Caltech on Thursday. I will no, tomorrow. So I can do the class in person at Caltech, and I will still leave it online available. So if you prefer to follow it online for you can use the same link as today to connect online if you prefer to do to follow this next lecture on Thursday online just for safety. So, but yeah, I think I should be able to also do it in person. I'll send a confirmation email to all of you on Thursday morning, or whether it will be both in person and online, or just online. But no, either way, I'll be there. Okay.
Thank you.
Thank you.
Okay.
Can I ask if you're coming tomorrow
yes.
to that?
Sorry.
No? Yeah, can you hear me?
Yes, I can.
I just wanted to ask if you'll be there tomorrow for that seminar on languages from enriched categories. I saw some announcement for PMA that there's a linguistics seminar.
Yeah, so
Um,
I will be at the seminar, because yeah, I can be at Caltech tomorrow. So I will be at the seminar. So the seminar will be there. I will be at the seminar, but I mean, I think I will keep some distance for just to be sure. But
okay. No, I was just asking because we've been discussing things like categories and language, and I was wondering if I might
yeah, I
speak to
think
you
at
a
the
bit there
seminar,
about.
I think you will you be at Caltech tomorrow? You going to the seminar?
Yes, I will try to come for that physically.
Yeah, because I mean, I think they will be interesting with that talk. There's some categorical constructions that are related to language that could be interesting to look at.
Right. I also wanted to ask if you might be able to send me some papers I could read. If for your presentation, maybe I can talk about some of this category stuff. I can get a chance to read some of
Okay.
these papers.
Okay, so yeah, there was this one I mentioned that's on the web page that does this more categorical form of the Chomsky-Schutzenberger theorem. Did you look at that? I mean, is that something that you would be interested in doing for the presentation?
I did read through the very first page of that, but um, I thought there might be more like a broader literature around it of using categories, not specifically for Chomsky's stuff, but for linguistics in general. And I was wondering if that kind of literature actually exists or not.
Yeah, so I do have to search a bit for whether there's something, because I don't have like a good like survey of in general about categories in linguistics that as I said, there are a few papers that use it, and I think this one would be like a good example for categorical result, but where you actually prove or reprove some nice result with this categorical language. So I thought that could be a good example of use of category theory in linguistics. I can look a little bit more, but I don't have like a good general survey of categorical use in uses of category theory in linguistics that I can suggest. Yeah, I can look a bit more if to see if there's some other papers that I can suggest besides that one.
Okay,
Okay.
the only reason I ask is because I mean it's not just that I want to see how categories are used. I would like to see where it's useful actually, and the things that you were talking about. That you said it might be useful some things that you suspect, um, and so
Yeah,
it
but
would be
that
nice
probably has
to.
to be, yeah, that's a chemical story that needs to be thought about. I mean, there's not much that's done already. So
Okay, so then tomorrow maybe I'll try and find you and
yeah,
discuss a bit.
yeah.
Okay, thank you.
Okay.